Hello and welcome to all students. In this lecture, we learn about the uh, limit limit of a real valued function. So let us define. There are two types of limit. First is one side limit, left hand side limit, and right hand side limit. So first of all, we define function f of x. First of all, we define left hand side limit. Function f of x is said to have left hand limit L as extends to real number a if for any given epsilon greater than 0 however small there exists delta greater than 0 very small such that whenever x is greater than a minus delta and less than a, this must implies mod of f of x minus L less than epsilon. So this is the mechanical definition, but the geometrical meaning of this definition is very simple. The function f of x is said to, the values of function f of x said to approaching towards L if x approaches a from the left hand side of a, okay, on the real line. So this is the very simple meaning of the left hand side limit. So in this case the value of x approaches to a from left side of a, and this left hand side of function so this left hand limit of function f of x is denoted by the notation limit f of x extends to a minus is equal to L. Now let us define the right hand side limit. Function f of x is said to have right hand limit L as extends to real number a if for any given epsilon greater than 0 however small there exists delta greater than 0 very small such that whenever x is greater than a and less than a plus delta, this must implies mod of f of x minus L is less than epsilon. But the geometrical meaning is once again very simple. So we say that the functional values or values of function f of x approaches towards the real number L if x approaches towards a from the right hand side of a on the real line. Okay, so this is the geometrical meaning, and in this case values of x approaches to a from right hand side of a. This left hand limit of function f of x is denoted by limit of f of x extends to a plus is equal to L. If note down, if both left hand limit and right hand limit of function f of x as extends to a exist and both are equal to L, then the limit of a function exists and is equal to L. So to exist a limit of a function f of x, it is necessary to exist a left hand limit of that function and right hand limit of that function. That is, if limit of f of x extends to a minus equal to L and limit of f of x extends to a plus is equal to L, then we say that limit of that function f of x as extends to a is equal to L. Now let us see one example. Consider a function y equal to mod x and it is defined for all real numbers. Here from the graph we can observe that the left hand limit is so limit of function mod x as extends to 0 minus means x approaching towards 0 from the left hand side of 0, and as x approaches towards 0 the values of function approaches towards 0, okay, or the graph of function approaches towards 0. So limit of mod x as extends to 0 minus is equal to 0, and similarly the right hand limit is limit of mod x as extends to 0 plus and it is equal to 0 again because as x approaches towards 0 on from the right hand side of 0, the graph of that function also approaches towards 0, or the values of function approaches towards 0. Okay, so therefore the left hand limit and right hand limit, both limit exist at x is equal to 0 there, and it is equal to 0. Therefore the limit of function mod x as x tends to 0 is 0. Okay, so this is a very simple example for the one side limit. Now let us go to the limit at infinity and infinite limit. Limit at plus infinity. A function f of x is said to have limit L as x tends to infinity if for any given epsilon greater than 0, however small, there exists a big number m greater than 0 such that whenever x is greater than m, this must implies distance between f of x and L is less than epsilon. So mod of f of x minus L is less than epsilon. So meaning of this thing is, we say that functional values or values of function f of x approaches towards a real number L, if x becomes larger and larger. Okay, so as m is a very big number, and for all values of x which is greater than m, this must implies the distance between f of x and L is less than epsilon. Okay, in this case we say that limit of a function f of x is L as x tends to infinity, okay, plus infinity. This limit is denoted by notation limit of f of x tends to infinity is equal to L. Okay, limit of f of x tends to infinity is equal to L. This means whenever x becomes larger and larger, value of function f of x approaches to a real number L. Whenever x becomes larger and larger, the values of function f of x approaches to a real number L. Okay. So let us take one example. So limit as x tends to infinity of a function x into sin 1 by x is equal to 1. Okay. Limit at infinity and infinite limit. A function f of x is said to have a limit L as x tends to minus infinity if for any given epsilon greater than 0, however small, there exists a big number m greater than 0 whenever x is less than minus m. This must implies the distance between mod of f of x minus L is less than epsilon. So limit at infinity means we say that the limit of a function f of x as x tends to minus infinity is L if whenever x becomes smaller and smaller, the values of function f of x approaches towards L. So that, or we can say that when x tends to minus infinity, the distance between f of x and L becomes smaller and smaller. So in this case we say that the limit of function f of x this limit is denoted by limit of f of x tends to minus infinity is equal to L. This means whenever x becomes smaller and smaller, value of function f of x approaches to a real number L. For example, limit of the function e raised to the power x as x tends to minus infinity is equal to 0. Okay, as x becomes smaller and smaller, the functional values of function e raised to the power x approaches towards 0. A function f of x limit plus infinity. A function f of x is said to have limit plus infinity as x tends to a real number a. A function f of x is said to have limit plus infinity as x tends to a real number a if for any given big real number k greater than 0 there exists a delta greater than 0, delta is very small, such that whenever distance between x and a is greater than 0, less than infinity, this implies that the values of function f of x is greater than k. Means whenever x approaches towards a, this implies that f of x becomes larger and larger. Okay, in this case we say that limit of function f of x is infinity as x tends to a. As x tends to a. This limit is denoted by limit of f of x tends to a, and it is equal limit of f of x tends to a equal to plus infinity. This means whenever x approaches to a real number a, then values of function f of x becomes larger and larger. This means whenever x approaches to a real number a, then values of function f of x becomes larger and larger. For example, limit of tan x tends to pi by 2. For example, limit of tan x tends to pi by 2 is equal to plus infinity. A function f of x is said to have limit plus minus infinity. A function f of x is said to have a limit minus infinity as x tends to a. As x tends to a real number a, if for any given big real number k greater than 0, there exists a delta greater than 0, delta is small, such that whenever distance between x and a is small, this implies that f of x is less than minus k. This means that the limit of, we say that limit of f of x is minus infinity as x tends to a if whenever distance between x and a is small, value of f of x becomes smaller and smaller. This limit is denoted by limit of f of x tends to a equal to minus infinity. This means whenever x approaches to a real number a, then values of function f of x become smaller and smaller. Let us take one example. Limit tan x tends to minus pi by 2 is minus infinity. So let us take one example now. Show that question number 1, show that limit x tends to 0 plus of function 1 upon x is equal to infinity, and limit x tends to 0 minus of function 1 upon x is minus infinity. What can you say about limit of 1 upon x tends to 0? Okay, so let us take a part 1. We show that limit of 1 upon x tends to, as x tends to 0 plus is infinity, that is, we show that for any given big m greater than 0, for any given big number m greater than 0, there exists delta greater than 0, such that whenever x is greater than 0 and less than delta, this must implies 1 upon x is greater than m. So consider now x is less than delta. So this will implies 1 upon x will be greater than 1 upon delta, and therefore we choose delta is equal to 1 upon m, and this implies that 1 upon x is greater than m, and this shows limit 1 upon x extends to 0 plus is equal to infinity. So m is very big number and 1 upon x is greater than that big number. That's means that m is any big number. So we say that values of 1 upon x approaching towards plus infinity. Now consider the part number 2. Part number 2. Here we show that limit of the function 1 upon x, limit of the function 1 upon x as extends to 0 minus is equal to minus infinity, and for that is we show that for any given big number m greater than 0, there exists a delta greater than 0. It is a small such that whenever x is greater than minus delta and less than 0, x is greater than minus delta and less than 0, this must implies 1 upon x is less than minus m. Okay, so now consider for that minus delta is less than x. So this implies that minus 1 upon delta is greater than 1 upon x, and that is 1 upon x is less than minus 1 upon delta. So therefore we choose delta to be 1 upon m, and this shows that 1 upon x is less than minus m. This implies that limit of 1 upon x extends to 0 minus is equal to minus infinity, and we in part 3 we make the conclusion from step 1 and step 2. The conclusion is that both limits are not same, left hand side limit and right hand side limit both are not same. Therefore this shows that limit 1 upon x extends to 0 does not exist. Okay, so this is the end of our lecture, and let us stop here, and the remaining part we will see in the